Everything you see, everything you touch is made of something. That something is made of even smaller things. If you keep zooming in, past the fabric, past the fibers, you eventually arrive at the fundamental building blocks of matter. We call these atoms. An atom is an astonishingly small particle, the smallest unit of an element that retains that element's properties. Imagine a single grain of sand. It contains more atoms than there are grains of sand on all the beaches of Earth. At the very center of this tiny universe is a dense core called the nucleus. This nucleus houses particles known as protons, which have a positive charge, and neutrons, which have no charge at all. They are huddled together, forming the atom's heavy, stable heart. Swirling around this central nucleus, in a vast expanse of mostly empty space, are the electrons. These are the particles that truly define an atom's personality. Electrons are incredibly lightweight. They carry a negative charge. It's the attraction between the positive protons in the nucleus and the negative electrons that holds the entire atom together. To understand how atoms interact, we need to know where their electrons are. Think of it like knowing someone's address. For electrons, this address is called the electron configuration. It's a notation that tells us exactly how the electrons are distributed among the various shells and orbitals. Each orbital is like a small room within a larger floor, a subshell on a specific level of a building, a shell. The lowest energy shell, shell 1, contains one spherical s orbital. Shell 2 has a 2s orbital and 3 dumbbell-shaped p orbitals, px, POY, p occurs. The s orbital holds up to 2 electrons. The 3 p orbitals together hold up to 6 electrons. Back to carbon. Carbon has 6 electrons to place. First 2 go into 1s, next 2 fill 2s. 2 remain. Those 2 occupy 2 separate 2p orbitals. Carbon's full configuration, 1 squared, 2 squared, 2p squared. Superscripts show electron counts. It's a map of the atom's electronic structure and explains chemical reactivity. As electrons fill up the available orbitals according to Hund's rule, something interesting happens. There are certain arrangements that result in extra stability for the atom. One of these special cases is when a subshell is exactly half filled. P orbitals, d orbitals. This means every orbital in that subshell contains a single electron, and all these electrons have the same spin. For example, a nitrogen atom has 7 electrons, with a configuration of 1s squared, 2s squared 2p3, show orbital diagram. The 3 electrons in the 2p subshell occupy the 3 separate p orbitals, 1 in each. This half-filled 2p subshell gives nitrogen surprising stability. Why is this arrangement so stable? There are a couple of reasons rooted in quantum mechanics. First, having electrons in separate orbitals minimizes electrostatic repulsion. Electrons are negatively charged, and like charges, repel. By keeping them in different rooms, the atom reduces internal pushing and shoving, lowering overall energy. Imagine 3 people who would rather not sit next to each other. Giving them each their own couch is more stable than forcing them to share one. The atom feels the same way about its electrons. Second, a quantum effect called exchange energy. Atoms, in a way, are a bit like people. They seek stability. For many of the elements we encounter most often, this stability is found in a simple, elegant pattern known as the octet rule. This rule observes that atoms tend to gain electrons, lose electrons, share electrons in order to achieve a full outer shell containing 8 electrons. Why 8? Because this is the electron configuration of the noble gases, like neon, argon. These elements are famously noble or inert because they are electronically content. Their full outer shells make them extremely stable and non-reactive. Other atoms look at the noble gases with a kind of electronic envy and will go to great lengths to mimic their configuration. This drive to complete the octet is the primary motivation for the formation of chemical bonds. Atoms that are not noble gases are inherently unstable on their own. They can achieve stability by teaming up. For example, consider sodium, which has just one electron in its outer shell. It can easily lose this lone electron, exposing the full shell underneath, which has 8 electrons. Now consider chlorine, which has 7 electrons in its outer shell. It is just 1 electron shy of a full octet. It has a strong desire to gain 1 more electron to complete its shell. When a sodium atom meets a chlorine atom, it's a perfect match. Sodium happily gives its electron to chlorine, and in doing so, both atoms achieve a stable octet. This process of gaining, losing, sharing electrons is quantified by an atom's valency. Valency is the bonding capacity of an atom. It's the number of electrons it needs to give away, accept, or share to reach that stable octet state. Oxygen, with 6 outer electrons, needs to gain 2 more, so its valency is typically 2. Carbon, with 4 outer electrons, is in a unique position. It can either lose 4 or gain 4, but it more commonly shares 4 electrons, giving it a valency of 4. This concept of valency allows us to predict how atoms will combine. An oxygen with valency 2 will combine with 2 hydrogens with valency 1 each to form a stable water molecule. When atoms form bonds, they create a new entity, a molecule or a compound that is more stable than the individual atoms were on their own. This increased stability means the compound has lower overall energy. Nature always favors lower energy states. A ball rolls downhill, not uphill. Similarly, atoms bond to roll down an energy hill to a more stable resting place. Whether they do this by transferring electrons to form ionic bonds, like in salt, or by sharing electrons to form covalent bonds like in water, the end goal is the same: to achieve a stable electron configuration, most often the celebrated octet, and settle into a state of lower energy. The strange and wonderful rules of quantum mechanics are not just abstract ideas. They are the architects of the material world. The concept that an electron's position is a cloud of probability, not a fixed point, is what gives orbitals their shapes. Orbital shapes determine how atoms connect. They dictate molecular geometry. They dictate crystal structure. Stability of a compound follows from these quantum interactions. When atoms bond, their electron probability clouds overlap and merge. Electrons occupy a new, lower energy arrangement that spans both nuclei. That lowered energy holds atoms together in a stable embrace. All these principles are interconnected in a beautiful dance of physics. The atomic number sets the cast. The number of electrons. Hund's rule. Pauli exclusion principle. The quest for stability is guided by the octet rule. Half-filled orbitals also have special stability. Valency acts as the script for partnerships and ratios. The whole performance happens in a probabilistic, quantized world. Energy levels are fixed, electron locations are fuzzy. This explains why some atom combinations are stable and others are not. Example: table salt, sodium chloride. Sodium has 1 outer electron. Chlorine has 7. Alone, both are unstable and reactive. When they meet, quantum rules decide. The octet rule: sodium wants to lose an electron. Chlorine wants to gain an electron. The electron jumps. Sodium becomes a positive ion with a full outer shell. Chlorine becomes a negative ion with a full octet. Opposite charges attract. Ionic bond forms. The salt crystal is far lower energy and very stable.